I want to go back to the quadratic equation that we solved in the last video. It was 2x squared plus 5x minus 3. We factored it, set each factor to 0, and got two answers. And so I always like to talk about this in class because I don't know if this struck you, but here's an equation math equation with two answers to it. You know, how many problems have you seen that have two answers? And here's such an example. There are actually equations with three answers, or four answers, or as many as you like. And in fact, there are some problems, and some equations in mathematics, which have infinitely many answers. Let me give you an example. In trigonometry, the sine of x equals to 1/2. The sine function is related to triangles and angles. This has actually infinitely many answers to it. One answer is 30 degrees. Another answer is 150 degrees. And then if you go around the circle 360 degrees, add 360 to this, you get 390. And here you get 510. And it just goes on forever. Every time you go around a circle, you pick up two more answers to this equation. You can go backwards around the circle. So this equation has infinitely many answers, which I think is kind of interesting. All right, and usually we're only interested in one or two of these answers, but so there are two answers to this problem, and I want you to see why there is from a different aspect of this. I want to show you the geometry of this problem. And if I were to set this polynomial, this quadratic polynomial, equal to y, and for the moment, let's just concentrate on this function. Y equals to 2x squared plus 5x minus 3. Forget the equal 0 for the moment. It could be written as a function. You might remember functions from early in the course. Y and f of x. This could be f of x equals to 2x squared plus 5x minus 3. As a function with x's and y's, we can draw a graph. And here's what the graph looks like. So, and I'm just going to kind of sketch it here. It won't be that precise. All right, so it turns out that this function, its graph, crosses the x-axis at -3 and at 1/2. And it also happened to have a y-intercept of -3. So now I'm not sure exactly how far down it goes, but it's a curved shape that sort of arches, goes down, then loops back up again. And that's a shape called a parabola. Parabolas were known to the ancient Greeks. They had actually two ways of defining parabolas that I'm aware of. They defined parabolas as a conic section, and also in terms of another geometric property. These properties are what you would see if you take our trigonometry course, because we study the conic sections. We study circles and ellipses, which are ovals. We study hyperbolas, which are kind of strange two-part pieces, shapes. And we also study parabolas. And so parabolas have some rather unique qualities. In fact, if you take a parabola and spin it, and normally when this is done, the shape is flatter. If you were to take this parabola and spin it, you would create a sort of a parabolic dish. And that's the shape that's used in satellite dish antennas. And not all satellite dish antennas are truly parabolic. Some of them are not quite so symmetrical, but they all have the same geometric property in that they concentrate the signals coming into the dish into a single point, and that's where all the electronics are inside the dish. All right, I could say a lot about this. But you also see parabolas when things fly through the air. You know, if I just toss this pin through the air, watch it carefully. I'll do it again. Whoops, one more time. All right, so that arc is a parabolic arc. It is a parabola. It forms a parabola shape with all the geometric properties that parabolas are supposed to enjoy as it flies through the air. And so they're really quite common. And when you think about it, you know, this is 1 degree higher than a linear equation, you know, just a first degree equation. So it's the next step up in complexity. Now, to this point here, the parabola, because it dips down and comes back up again, in this case, it has to cross the y-axis in 2 places. I'm sorry, the x-axis in 2 places. And it crosses at -3 and 1, also positive 1/2. And so when you set this equal to 0, you're trying to find out, well, where is y equal to 0? Well, where is y equal to 0? It's right here along this x-axis. And so setting y equals to 0 means you're asking, where does this coincide with the x-axis? Where does it cross the x-axis? It has to cross in 2 places. So that's why we normally get 2 answers to these quadratic equations. And so now it's possible to get 1 answer to a quadratic equation if your quadratic equation just touches the axis once, then you get a single answer. You know, that's a pretty special case. And if you have a quadratic equation or a quadratic function which does not cross the x-axis, it turns out that we get complex numbered answers. And so that's why complex numbers were introduced to you in the previous chapter, is so that we can solve equations where if you looked at it in the function form, the parabola would never cross the x-axis. It could also go upside down and miss the x-axis. And those turn out to have complex number answers. So anyway, a little bit of the geometry of why we're getting 2 answers. I think this is important to see this because algebra and geometry are actually much more closely related than most people realize. And that connection was not really established until the early 1600s when René Descartes came up with the xy plane, what we call also the Cartesian plane. And so then we were able to start linking algebra and geometry together. Before then, I'm not sure that many people realized, even thought there was even remotely any connection between algebra and geometry. So it turns out that we can understand a lot of algebra through the geometry of the algebra, and vice versa. We can look at geometry and begin to understand it through the algebra. So an important point to make, and one, if you take more math, you'll begin to see more and more. In fact, if you take calculus, calculus goes quite heavy into these ideas of linking geometry with the algebra.